Not all fat is the same, and that distinction is not cosmetic, it is biological. The fat visible under the skin, subcutaneous fat, is largely inert. It sits there. It doesn't do much. But visceral fat, the fat packed around the liver, the pancreas, the intestines, deep inside the abdominal cavity, is metabolically active. It behaves less like a storage depot and more like a dysfunctional organ. It secretes inflammatory molecules. It disrupts hormonal signaling. It drives insulin resistance, cardiovascular disease, type 2 diabetes, and certain cancers, independently of body weight. A person can be at a normal body weight and still carry dangerous levels of visceral fat. The scale doesn't tell that story. Here is what the science says about reducing it, specifically, efficiently, and sustainably. Before addressing solutions, the biology needs to be understood. Because visceral fat doesn't accumulate randomly, it accumulates in response to specific, identifiable physiological signals. Visceral fat cells, called visceral adipocytes, are fundamentally different from subcutaneous fat cells. They have a higher density of cortisol receptors and glucocorticoid receptors, making them disproportionately responsive to stress hormones. Every time cortisol spikes, through chronic stress, poor sleep, or blood sugar crashes, visceral adipocytes receive a preferential signal to store fat. They also have a higher density of beta-3 adrenergic receptors, which means they are theoretically more responsive to fat mobilization signals. This is actually good news. It means visceral fat, despite being dangerous, is also more metabolically accessible than subcutaneous fat under the right conditions. The third key factor is insulin. Visceral fat is exquisitely sensitive to insulin levels. Chronically elevated insulin, driven by refined carbohydrates, frequent eating, and sedentary behavior, locks visceral adipocytes in storage mode. When insulin is high, fat release is biochemically suppressed. It doesn't matter how little someone eats. If insulin remains chronically elevated, visceral fat reduction is severely blunted. Understanding this triangle, cortisol, beta-adrenergic signaling, and insulin, is the foundation of every effective strategy that follows. Dietary intervention is the most powerful lever for visceral fat reduction, but the type of dietary change matters enormously, and the popular advice is often imprecise. First, insulin management, not calorie obsession. A meta-analysis published in the British Medical Journal comparing low-carbohydrate diets to low-fat diets showed that low-carbohydrate approaches produce significantly greater reductions in visceral fat, even when total caloric intake was similar. The mechanism is straightforward. Reducing refined carbohydrates lowers insulin, which unlocks visceral adipocytes and allows fat mobilization to occur. This does not mean eliminating carbohydrates entirely. It means a strategic reduction in the foods that produce the highest and fastest insulin responses: white bread, white rice, sugary beverages, pastries, ultra-processed snack foods, sweetened cereals. These are the primary drivers of the chronic hyperinsulinemia that traps visceral fat in place. Second, prioritize protein. Protein has the highest thermic effect of any macronutrient. Approximately 20 to 30% of its caloric content is burned during digestion and processing. More importantly, adequate protein intake preserves lean muscle mass during a caloric deficit. Muscle tissue is metabolically expensive. It increases basal metabolic rate and improves insulin sensitivity at the cellular level. Losing muscle while reducing fat is a metabolic regression. A target of 1.6 to 2.2 grams of protein per kilogram of body weight per day is well supported by the literature for body composition optimization. Sources: eggs, wild fish, legumes, Greek yogurt, poultry, and quality red meat in moderation. Third, fiber, particularly soluble fiber. Soluble fiber forms a viscous gel in the intestine that slows glucose absorption, blunts insulin spikes, and feeds the gut bacteria that produce short-chain fatty acids, compounds that directly improve insulin sensitivity in liver and muscle cells. A study published in Obesity found that every 10-gram increase in soluble fiber intake per day was associated with a 3.7% reduction in visceral fat accumulation over 5 years, independent of total caloric intake. Sources: oats, flax seeds, psyllium husk, legumes, apples, and Brussels sprouts. Exercise reduces visceral fat, but not all exercise equally, and the popular intuition about which type works best is frequently wrong. High-intensity interval training, HIIT, produces the greatest visceral fat reduction per unit of time invested. A meta-analysis published in the British Journal of Sports Medicine analyzed 39 studies and found that HIIT was significantly more effective than moderate-intensity continuous training for reducing visceral fat, even when the total caloric expenditure was lower. The mechanism operates through two pathways. During HIIT, catecholamines, epinephrine and norepinephrine, spike dramatically. These hormones bind to the beta-3 adrenergic receptors on visceral adipocytes and trigger fat mobilization preferentially from visceral depots. After the session, the body enters a state of elevated post-exercise oxygen consumption, EPOC, during which fat oxidation remains elevated for 12 to 48 hours. 3 sessions of 20 minutes of HIIT per week, alternating 30 to 40 seconds of maximum effort with 90 seconds of recovery, is sufficient to produce measurable visceral fat reduction within 8 weeks in clinical trials. Resistance training plays a complementary role. It doesn't reduce visceral fat as directly, but it builds muscle mass that improves insulin sensitivity chronically, addressing one of the root biological drivers. A combination of 2 HIIT sessions and 2 resistance training sessions per week represents the evidence-based optimum. Walking should not be dismissed either. Studies consistently show that 7,000 to 10,000 steps per day reduces visceral fat independently of structured exercise, primarily through its effect on blood glucose regulation and chronic cortisol levels. Sleep deprivation is one of the most potent drivers of visceral fat accumulation and one of the most consistently ignored. A landmark study from the Annals of Internal Medicine placed participants on identical caloric deficits but varied their sleep duration. Those sleeping 8.5 hours per night lost 55% more body fat than those sleeping 5.5 hours, and crucially, the sleep-deprived group lost predominantly lean muscle mass rather than fat. The mechanisms are layered. First, cortisol. Sleep deprivation elevates cortisol chronically, which preferentially directs fat storage toward visceral depots. Second, ghrelin and leptin dysregulation. Poor sleep increases ghrelin, the hunger hormone, and suppresses leptin, the satiety hormone. This creates a biological environment that drives overeating, particularly of high-calorie, high-sugar foods. Third, insulin sensitivity drops measurably after even a single night of poor sleep. 7 to 9 hours of quality sleep per night is not a lifestyle preference. It is a metabolic requirement for visceral fat reduction. Addressing sleep architecture, consistent sleep and wake times, a cool and dark room, no screens for 60 minutes before bed, no alcohol within 3 hours of sleep, is as important as any dietary or exercise intervention. Chronic psychological stress is a direct cause of visceral fat accumulation, not a metaphor, not a contributing factor, a direct cause. When the stress response is activated, cortisol mobilizes energy by raising blood glucose. If that glucose is not used, because the stressor is psychological, not physical, insulin is released to manage it. Over time, repeated cortisol spikes in sedentary individuals create a cycle of insulin dysregulation and preferential fat deposition in visceral depots. Research published in Psychosomatic Medicine showed that individuals with high cortisol reactivity to stress had significantly greater visceral fat accumulation over time, independent of diet and exercise. The interventions with the strongest evidence for cortisol reduction are mindfulness-based stress reduction, practiced for 20 minutes daily over 8 weeks, has been shown in clinical trials to measurably reduce cortisol levels and visceral fat. Zone 2 cardiovascular exercise, low-intensity, sustainable aerobic activity, also reduces baseline cortisol and improves HPA axis regulation. And social connection, which is consistently underestimated in metabolic health research, has been shown to blunt cortisol responses to stress at the hormonal level. Beyond macronutrient strategy, specific foods have demonstrated direct effects on visceral fat in clinical studies. Green tea, EGCG, combined with caffeine, has been shown in a meta-analysis of 15 randomized controlled trials to produce a small but statistically significant reduction in visceral fat, independent of caloric restriction. The mechanism involves increased fat oxidation and improved insulin sensitivity. Vinegar, specifically acetic acid. A Japanese clinical trial published in Bioscience, Biotechnology, and Biochemistry showed that 15 milliliters of apple cider vinegar consumed daily for 12 weeks reduced visceral fat area by approximately 5% compared to placebo. The mechanism? Acetic acid suppresses fat accumulation by activating AMPK, the same cellular energy sensor activated by exercise and metformin. Fatty fish. EPA and DHA from wild salmon, sardines, and mackerel have been shown to reduce visceral fat through their effect on adiponectin, a hormone secreted by fat tissue itself that improves insulin sensitivity and promotes fat oxidation. Low adiponectin is directly associated with excess visceral fat. Omega-3s reliably raise it. Capsaicin, the active compound in chili peppers, activates thermogenesis and has shown modest but consistent effects on visceral fat reduction in multiple short-term trials, primarily through sympathetic nervous system activation and increased energy expenditure. Alcohol deserves specific attention in the context of visceral fat because its effects are frequently minimized. Alcohol is preferentially metabolized by the liver, and when consumed regularly, it promotes hepatic lipogenesis, the production of fat in the liver, and directly increases visceral fat deposition. The term beer belly is not cultural mythology. It reflects a documented biological reality. Even moderate alcohol consumption, defined as 1 to 2 drinks per day, has been associated in longitudinal studies with measurably greater visceral fat accumulation compared to non-drinkers, after controlling for caloric intake. The mechanism extends beyond calories. Alcohol disrupts sleep architecture, elevates cortisol, impairs insulin sensitivity, and suppresses fat oxidation for up to 24 hours after consumption. Every one of these effects directly opposes visceral fat reduction. Visceral fat responds to specific, targeted interventions, not generic advice. Lower insulin through strategic carbohydrate reduction. Maintain protein intake to preserve muscle and metabolic rate. Add soluble fiber to blunt glucose spikes and feed a healthy microbiome. Prioritize HIIT and resistance training over long, low-intensity cardio sessions. Protect sleep duration and quality with the same discipline applied to diet. Manage cortisol, because stress is not a psychological issue, it is a metabolic one. The biology of visceral fat is well understood. Its reduction is not a mystery. It is the predictable outcome of applying consistent, evidence-based pressure across these interconnected systems, simultaneously, not sequentially. The body responds. The timeline is measured in weeks, not years, when the right variables are addressed at once.